Hello friends, welcome to this YouTube channel. Today we are going to solve a pair of numerical problems on three-phase induction motors. By solving these problems, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor for a particular value of slip using its per phase approximate equivalent circuit when values of no load current and circuit parameters are given. A three-phase 440 volt 50 Hz 4-pole star-connected induction motor has following per phase parameters referred to stator side. R1 equals to 0.1 ohm, X1 equals to 0.4 ohm, R2 dash equals to 0.15 ohm, and X2S dash equals to 0.44 ohm. The stator core losses amount to 1250 watts and the rotational losses equal 1000 watts. At no load, the motor draws a line current of 20 ampere at a power factor of 0.09 lagging. When the motor operates at a slip of 3% using approximate equivalent circuit, we have to calculate rotor speed, input line current and its power factor, developed torque, shaft torque and efficiency. Let us first write down the given data. For stator winding, resistance per phase R1 equals to 0.1 ohm and leakage reactance per phase X1 equals to 0.4 ohm. Expression for stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.1 plus J times 0.4 ohm. For rotor winding, given resistance per phase referred to the stator R2 dash equals to 0.15 ohm and standstill leakage reactance per phase X2S dash equals to 0.44 ohm. For any value of slip S, rotor impedance per phase referred to stator side Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 3%, that is equal to 0.03 per unit. Therefore, Z2 dash equals to 0.15 by 0.03 plus J times 0.44 ohm. That gives us 5 plus J times 0.44 ohm. Let us now determine equivalent impedance per phase. ZEQ equals to Z1 plus Z2 dash. Using values we get 5.1 plus J times 0.84 ohm. This may be written in polar form as 5.1687 ohm at an angle 9.353 degree. Given line-to-line terminal voltage VL equals to 440 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 440 divided by root 3, that gives us 254 volts. We have determined equivalent impedance per phase ZEQ equals to 5.1687 ohm at an angle 9.353 degree. Let us now calculate rotor current per phase referred to stator side. I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 254 at an angle 0 degree divided by 5.1687 at an angle 9.353 degree. That gives us 49.142 ampere at an angle minus 9.353 degree. Given no load line current I0 equals to 20 ampere. For star connected induction motor, no load line current equals to no load phase current. Given no load power factor cos phi 0 equals to 0.09 lagging. Let us now determine no load power factor angle. Phi 0 equals to cos inverse 0.09, that is equal to 84.8364 degree. No load current may be written in polar form as I0 equals to I0 at an angle minus phi 0, that is equal to 20 ampere at an angle minus 84.8364 degree. This may be written in Cartesian form as 1.8 minus j times 19.91884 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 49.142 ampere at an angle minus 9.353 degree. This may be written in Cartesian form as 48.4887 minus j times 7.98639 ampere. Applying Kirchhoff's current law, we get input current per phase I1 equals to I0 plus I2 dash. Using values, we get 50.2887 minus j times 27.90523 ampere. This may be written in polar form as 57.51222 ampere at an angle minus 29 degree. In polar form, we can write input current per phase I1 equals to I1 at an angle minus phi 1 equals to 57.51222 ampere at an angle minus 29 degree. For star connected induction motor, input current per phase I1 equals to input line current. Now we shall calculate input power factor. Cos phi 1 equals to cos of 29 degree, that is equal to 0.87462 lagging. For three-phase induction motor, total input power Pin equals to root 3 times VL into I1 cos phi 1. Using values, we get root 3 into 440 into 57.51222 into 0.87462, which is approximately equal to 38,334.768 watt. Now we shall determine stator copper loss. PS copper equals to 3 times I1 square into R1. Given stator resistance per phase R1 equals to 0.1 ohm. Therefore, PS copper equals to 3 into 57.51222 square into 0.1, which is approximately equal to 992.3 watt. Now we shall calculate total stator losses. PS equals to PSI plus PS copper. Given stator core losses, PSI equals to 1250 watts. Therefore, PS equals to 1250 plus 992.3, that is equal to 2242.3 watt. Now we shall calculate total air gap power. Pg equals to Pin minus Ps. Using values we get 38,334.768 minus 2,242.3. That gives us 36,092.468 watt. We have obtained total air gap power Pg equals to 36,092.468 watt. Let us now determine total mechanical power developed. Pm equals to 1 minus S times Pg. Given slip S equals to 0.03 per unit. Therefore, Pm equals to 1 minus 0.03 into 36,092.468, which is approximately equal to 35,010 watts. Now we shall calculate total shaft power output. PO equals to Pn minus PR. Given rotational losses, PR equals to 1000 watts. Therefore, PO equals to 35,010 minus 1000, that gives us 34,010 watts. Now we shall determine overall efficiency of the motor. Eta equals to PO divided by Pin. We have computed total input power Pin equals to 38,334.768 watt. Therefore, eta equals to 34,010 divided by 38,334.768, that is equal to 0.8872 per unit or 88.72%. Given number of poles of the machine P equals to 4 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 4, that gives us 1500 revolutions per minute. Now we shall determine rotor speed. Nr equals to 1 minus S times Ns. Given slip S equals to 0.03 per unit. Therefore, Nr equals to 1 minus 0.03 into 1500, that is equal to 1455 revolutions per minute. Expression for developed torque. Td equals to Pg divided by 2 pi into Ns by 6T. We have obtained air gap power Pg equals to 36,092.468 watt. Therefore, Td equals to 36,092.468 divided by 2 pi into 1500 by 6T, which is approximately equal to 230 Newton meter. Now we shall calculate shaft torque. TSH equals to PO divided by 2 pi into Nr by 6T. We have determined shaft power output. PO equals to 34,010 watts. Therefore, TSH equals to 34,010 divided by 2 pi into 1455 by 6T, which is approximately equal to 223.2 Newton meter. A three-phase 440 volts 60 Hz star-connected 4-pole induction motor has following per-phase parameters referred to stator side. R1 equals to 0.1 ohm, X1 equals to 0.35 ohm, R2 dash equals to 0.12 ohm, and X2S dash equals to 0.4 ohm. The stator pole losses amount to 1200 watts and the rotational losses equal 950 watts. At no load, the motor draws a line current of 18 ampere at a power factor of 0.089 lagging. When the motor operates at a slip of 2.5%, using approximate equivalent circuit, we have to determine rotor speed, input line current, and its power factor, develop torque, shaft torque, and overall efficiency. Let us first write down the given data. For stator winding resistance per phase, R1 equals to 0.1 ohm and leakage reactance per phase, X1 equals to 0.35 ohm. Stator impedance per phase, Z1 equals to R1 plus JX1 equals to 0.1 plus J times 0.35 ohm. For rotor winding, given resistance per phase referred to the stator, R2 dash equals to 0.12 ohm and standstill leakage reactance per phase, X2S dash equals to 0.4 ohm. For any value of slip S, rotor impedance per phase referred to the stator, Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 2.5%, that is equal to 0.025 per unit. Therefore, Z2 dash equals to 0.12 by 0.025 plus J times 0.4 ohm. That gives us 4.8 plus J times 0.4 ohm. Now we shall determine equivalent impedance per phase. ZEQ equals to Z1 plus Z2 dash. Using values we get 4.9 plus J times 0.75 ohm. This may be written in polar form as 4.957 ohm at an angle 8.7 degree. Given line-to-line terminal voltage VL equals to 440 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 440 divided by root 3, that gives us 254 volts. We have determined equivalent impedance per phase ZEQ equals to 4.957 ohm at an angle 8.7 degree. Expression for rotor current per phase referred to stator side, I2 dash equals to ET divided by ZEQ. Taking terminal voltage per phase ET as reference, we get I2 dash equals to 254 at an angle 0 degree divided by 4.957 at an angle 8.7 degree. That gives us 51.24 ampere at an angle minus 8.7 degree. For three-phase induction motor, total air gap power PG equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator, R2 dash equals to 0.12 ohm and slip S equals to 0.025 per unit. Therefore, Pg equals to 3 into 51.24 square into 0.12 by 0.025, which is approximately equal to 37,808 watts. Total mechanical power developed, Pm equals to 1 minus S times Pg. Using values we get 1 minus 0.025 into 37,808, which is approximately equal to 36,863 watts. Let us now calculate total shaft power output. PO equals to PM minus PR. Given rotational losses, PR equals to 950 watts. Therefore, PO equals to 36,863 minus 950, that is equal to 35,913 watts. Given no load line current I0 equals to 18 ampere. For star connected induction motor, no load line current I0 equals to no load phase current. Given no load power factor cos phi 0 equals to 0.089 lagging. Let us now determine no load power factor angle. Phi 0 equals to cos inverse 0.089, that is equal to 84.894 degree. No load current may be written in polar form as I0 equals to I0 at an angle minus phi 0, that is equal to 18 ampere at an angle minus 84.894 degree. This may be written in Cartesian form as 1.602 minus J times 17.93 ampere. We have determined rotor current per phase referred to stator side I2 dash equals to 51.24 ampere at an angle minus 8.7 degree. This may be written in Cartesian form as 50.65 minus J times 7.75 ampere. Applying Kirchhoff's current law at node P, we get input current per phase I1 equals to I0 plus I2 dash. Using values we get 52.252 minus J times 25.68 ampere. This may be written in polar form as 58.2214 ampere at an angle minus 26.1725 degree. For star connected induction motor, input current per phase equals to input line current. Let us now calculate input power factor. Cos phi 1 equals to cos of 26.1725 degree, that is equal to 0.8975 lagging. We have obtained input current per phase I1 equals to 58.2214 ampere. Let us now calculate stator copper loss. PS copper equals to 3 times I1 square into R1. Given stator resistance per phase R1 equals to 0.1 ohm. Therefore, PS copper equals to 3 into 58.2214 square into 0.1, which is approximately equal to 1017 watts. Now we shall calculate total stator losses. PS equals to PSI plus PS copper. Given stator core losses, PSI equals to 1200 watts. Therefore, PS equals to 1200 plus 1017, that is equal to 2217 watts. Now we shall calculate total input power. Pin equals to Pg plus Ps. We have computed total air gap power Pg equals to 37,808 watts. Therefore, Pin equals to 37,808 plus 2,217, that is equal to 40,025 watts. Now we shall determine overall efficiency of the motor. Eta equals to PO divided by Pin. We have computed total shaft power output. PO equals to 35,913 watts. Therefore, eta equals to 35,913 divided by 40,025, that is equal to 0.8973 per unit or 89.73%. Given number of poles of the machine P equals to 4 and supply frequency F equals to 60 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 60 divided by 4, that gives us 1800 revolutions per minute. Expression for rotor speed Nr equals to 1 minus S times Ns. Given slip S equals to 0.025 per unit. Therefore, Nr equals to 1 minus 0.025 into 1800, that gives us 1755 revolutions per minute. Expression for developed torque Td equals to Pg divided by 2 pi into Ns by 60. We have determined air gap power Pg equals to 37,808 watts. Therefore, Td equals to 37,808 divided by 2 pi into 1800 by 60, which is approximately equal to 200.58 Newton meter. Expression for shaft torque TSH equals to PO divided by 2 pi into Nr by 60. We have computed shaft power output. PO equals to 35,913 watts. Therefore, TSH equals to 35,913 divided by 2 pi into 1755 by 60, which is approximately equal to 195.4 Newton meter. So today we have solved a pair of numerical problems on three-phase induction motors. By solving these problems, we have learned how to compute overall efficiency and shaft torque of a three-phase induction motor for a particular value of slip using its per phase approximate equivalent circuit when values of no load current and circuit parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.